In this short video, I'm going to explain how banker algorithm works by illustrating it with an example. Here is the example that I'm going to use. Assume that you have three processes, P1, P2, and P3, and they are requesting to allocate instances of resources with three different types: resource type A, resource type B, and resource type C. Each resource type has a number of instances available. We have 10 units of A, 5 units of B, and 7 units of C. Just to give you an example of resource types, you can consider A as the number of pages of memory available, or B would be the number of giga cycles of CPU available, and C can be something like the number of files available or something similar to that as the resources that processes A, B, and C need. So given all of this, let's start by defining a vector and three matrices. In Banker's algorithm, we define the following data structures. One is the available vector, which tracks the currently available amount of each resource. It's going to be a vector in this case with three numbers in it. One for A, one for B, one for C. That means, how many of units we have available from each of the three resources, A, B, and C. Then we have a maximum matrix, which is let's say 2D array, that in our case, it's going to have three rows, one for each process, and three column, one for each resource type. Here is the given maximum matrix. As you see, this is already given by the question, by the assignment, by the, let's say, example, and then we don't need to calculate it. This is already given. And this is basically telling you that how many instances of each resource does a process need at most. And this is an a priori information that we must have in order to run Banker's algorithm that tries to keep the system in a safe state at all times and um, uh, avoid a deadlock condition. So based on this matrix content, I know that P1 needs at most seven units of A, 5 units of B, and 3 units of C. Similar for P2, and then for P3 we need 9 units of A at most, 5 units of B, and 2 units of C. So never in the lifetime of any of these processes, each of them can demand more than these maximum numbers. For example, if P3 wants to request more than 9 A's, that request will be immediately denied or rejected by the operating system. Then you have another matrix called allocation matrix that basically shows the current allocation for each process. In this example, we have three rows, one for each process, and three columns, one for each resource type. As an example, consider P3 row, the last row of this matrix. The numbers 3, 0, and 2 basically mean that P3 has already allocated 3 units of A and 2 units of C, and P3 has not allocated any units of B because you see a 0 in this column, in column B. And given all of this, we will answer some questions. I forgot to tell you about the need matrix. That's going to be something that we will fill out ourselves based on the formula that I'm going to explain right now. Need basically would be a matrix that shows how much more each process needs of each resource type. For example, how many more A's does P1 need? And we're going to place it here. In order to find out the value or the number of units that P1 needs from A resource type, I need to subtract the current allocation of A resources in P1 from the maximum need of P1 for A. So the value for this cell would be this cell minus this cell, which is going to give me 7. If I do the same thing for other cells, I will get something like this, which basically says, for example, A needs at most 7 units of, I'm sorry, P1 needs 7 more units of A, 4 units of B, and 3 units of C. And then you can see it for other processes. So this matrix is basically equal to the maximum matrix minus the allocation matrix. That's how the matrices are subtracted in math. And then we use the same exact operation here to evaluate the value of matrix need. One more thing that we can also calculate is how much more or how many more units of each resource are remaining. Because we have the allocation matrix, and also we know the total number of units that are available for each of the resource types A, B, and C. It is possible to calculate the remaining number of units from resource A, resource B, and resource C. What's the formula? You need to basically subtract the sum of allocations of A from the total A. So the formula would be equal to this, which is the total units of A available, minus the sum of this column in the matrix of allocations, which basically adds up the total number of units of A that are allocated to P1, P2, and P3. If you do that, the answer would be 3. And if you do the same thing for the other types, you will get 3 and 4. So long story short, there will be 3 more A's, 3 more B's, and 4 more C's. For example, because we had a total of 7 C units, and one of them has been given to P2 and 2 of them has been given to P3, there will be 7 minus 1 minus 2 left, which is equal to 4. Then that's how we can calculate this remaining vector. Let's answer a few questions. The first question is this: use the banker's safety algorithm to find out whether the system is in safe state or not. So the safest state is nothing but a state in which the system has no chance of deadlock. That means the possibility of deadlock is 0 because of the a priori information that we have from each process. We know exactly how much they are going to request at most from each resource type. Let's see if this is an example of a safe state or an unsafe state. In order to figure it out, you need to come up with a safe sequence or try to come up with a safe sequence. Safe sequence is the order in which processes can be terminated. And then the safety algorithm in Banker's algorithm will basically tries to construct that safe sequence. If it can construct it, then the system is in a safe sequence. Otherwise, it is in an unsafe state. And that basically means there is a chance of deadlock in the future. All right, so let's see if we can answer this. I'm going to push these lines a little bit down so I can have some space to work with. All right, here it is. I'm going to start by constructing a work vector. And work vector would be a vector in which I know exactly how many units of A, B, and C I'm working with. And we initialize that to the number of available resources. That would be 3 A's, 3 B's, and 4 Cs. I told you how to calculate this available vector. That would be, as I said, the number of units of each resource that are available. We already calculated that. Now we're going to work with that. This is our work vector. That's the initial state. Now we try to see which process can be terminated. In order to terminate the process, you need to satisfy its maximum need. Here is the the matrix that shows the maximum needs of each process, P1, P2, and P3. I know that P1 needs this many of each resources, which is more than what I have to work with. And P3 needs 6A, 5Bs, but I only have 3A and 3Bs. So neither P1 nor P3 can be terminated at this time, but I can terminate P2. So I would say after P2 gets terminated, let's see what we have. Let's say P2, who needs less than what we have available, finish its job. When it finishes the job, then it will release its allocations. That's how allocation works in operating system. When a process dies, all the allocated resources will be freed, will be released by that process. So I need to add the current availability by the allocations of P2. And I do this not only for A, but for B and C. After this, my work vector has grown significantly. It is 7, 4, and 5. This number is not greater than the P3 maximum needs, because P3 need 5 Bs and I only have 4 of them, but it is exceeding or it's equal to at least the P1 needs. P1 needs 7A, I have 7As. P1 need 4 Bs, I have 4 Bs. P1 need 3 Cs, I have 5 Cs. So it's more than what P1 needs. So that means P1 can get terminated without any problem. And as I said before, it's going to release all of its allocations. So the previous work vector should be added by the amount of allocated resources by P1, and that would be 7As, 5Bs, and 5Cs after the execution of P1. Now, after P1 and P2 die, the only remaining process would be P3. Let's see if we have enough resources to terminate P3. P3's needs are less than or equal to what we have, so the answer is yes. And if you try to release the resources that are allocated by P3, what will happen is at the end, the number of resources would be exactly equal to what I had at the very beginning, which means I have 10A, 5B, and 7Cs at the end, which is equal to the total number of resources that we started with. So long story short, there is a safe sequence in which the processes can be terminated in that order with no shortage of resources. So the safe sequence would be P2, P1, and P3. If you would fail to construct this, you would say the system is in an unsafe state, but right now we would say the system is in a safe state. That means there is no chance of deadlock. And the operating system tries to avoid deadlock by keeping the system in a safe state. So any request that you make will be evaluated first. The operating system tries to see if that request is gonna keep the system in a safe state or if make it unsafe. If it makes it unsafe, then the request will be rejected. In order to illustrate that, I have the second part in this question, which is gonna exactly evaluate some of the requests to see if they can get granted or rejected by the operating system. The first one is P1 requesting 4 Bs. The next one is P2 requesting 2 As, and then the last one is P3 requesting 1 A and 1 B. Let's see if any of these will be accepted or granted, I should say. Before I move forward with solving these, let's look at this list that we need to follow whenever we want to check whether a request is granted. This is a checklist that you need to go through. If the request meets all the three and the checklist is completed successfully, then the operating system will grant the request. Otherwise, the operating system will reject the request. The first item in the checklist is this. Whatever the request you want to evaluate, like XYZ, should not exceed the currently available resources. In this example, we had 3 A's, 3 B's, and 4 C's. That was the available vector. And if, for example, X exceeds 3, X becomes more than 3, that means the amount of A's you need is more than 3, or Y exceeds 3, or Z exceeds 4, then you will immediately reject the request. Number 2, after the first checklist is passed, then you look at checklist number 2, or checklist item number 2, which says the request XYZ will be rejected if it exceeds the needs of a process, because each process has promised the maximum number of units for each process type. I mean, it has to adhere to that, or it has to follow that promise. So let's say P needs AAs, BBs, and CCs, but in the future, it requests something that exceeds any of these three numbers. That means the X amount of A's it requests exceeds A, or Y exceeds B, or Z exceeds C. In that case, we reject it. And then if the first two items in this checklist pass, then we're gonna check the last item, which is the most important one, I believe, because it's a little harder to verify that item in the checklist. It says you gotta assume that the request is granted. When you grant the request, then your allocation vector will be changed, because you need to increase the allocation vector for the requested process P by the values XYZ that is in the request. And then after you update the allocation matrix, then your need matrix will be updated as well. After you update the allocation matrix and the need matrix, then you run the safety algorithm of the bankers and then see if the system remains in a safe sequence or in a safe state by constructing a safe sequence. If you fail to construct a safe sequence, that means your state becomes your system's state becomes unsafe if you accept the request. Therefore, you have to reject the request, and you need to undo what you change in the allocation and needs matrices, because nothing has changed. You just there was a request, you rejected it, so you need to undo those changes. Let me use these to evaluate the three requests. The first one says P1 requests 4 instances of A. Let's go through this checklist. Does this request exceed the available resources? Let's see what's available. I have only 3 B's, and this one needs 4 B's. So this one is going to be rejected since it won't pass the first item in the checklist. So it was pretty easy, right? That was a pretty easy rejection. The next one says P2 requests 2 A's. And this time I can't reject it for the same reason, because we have enough A's. We have 3 A's, and then it only needs 2 A's. The next thing I need to check is, did P2 break its promise? P2 promised not to request more than 1 A and 2 B's and 2 C's in the future. But now it's asking for 2 A's, which exceeds the 1 A promised before. So that's another easy reject. It is rejected since it won't pass the second item this time in the checklist. And finally, let's do the last one. P3 request 1A and 1B. Does it satisfy or does it pass the first item in the checklist? Let's look at the availables and compare it with 1A, 1C. I'm sorry, 1A, 1B. Of course, this is greater than 1A, 1B, and 0Cs. In other words, in this case, I have XYZ equal to 1, 1, and 0. It only needs 1A and 1B, no, but no Cs. So in this case, it satisfies it passes the first item in the checklist. Does it pass the second item in the checklist? Let's look at the need for P3. It needs 6 A's and 5 B's. And if you look at what I have here, it's 1, 1. So that's pretty much less than what P3 needs. And that means the second item has been passed in the checklist. The remaining item would be the key. Does it pass the last item of the checklist? In order to find out, I have to go through the safety algorithm, which I did earlier. You remember we created a work vector and we just did some calculations. I'm going to do the same thing. So let me copy this and let's insert it here, paste it here. Let's move these down. Okay. And let's get rid of, well, we're gonna start from the same point. We have to work with 3 A's, 3 B's, and 4 C's because that's our available vector. Now let's see if we can come up with any safe sequence. Before I do that, I have to make the change. I have to add 1 A to the allocation vector of B and allocation vector of P3 and 1 B to the allocation vector of P3. So I need to increase this number and this number by 1. So let me make the changes. I'm just gonna make them yellow so you can see that we are changing them. So this becomes 4 and this becomes 1. So when I change these two, the needs have been updated as well automatically because Excel will basically run the formula immediately and it realizes that now your need has been reduced by 1 for A and 1 for B because it was 6, 5 before, now it's 5, 4. And that's pretty much the changes that I made. And then obviously it has to change the remaining A, B, and C. So you're not starting from 3, 3, 4 anymore. You should start from the 2 remaining one for A, 2 remaining one for B, and 4 remaining one for C. So the work vector always gets initialized by the available vector. But from now on, I need to come up with a safe sequence. Let's see which of these 3 or, which of the 3 processes we have, P1, P2, P3, can be satisfied with the values that we currently have in the work vector. So if you look closely among these 3 rows, only P2 can be satisfied because P2 needs 1A, 2B, and 2Cs. So we can terminate P2 because it needs less than or equal to what we have. And then, like always, you have to release all the allocations for P2 when you terminate it. If you do that, then after P2, you have this many A, B, and C available. 6 A's, 3 B's, and 5 C's. This is greater than, or the question is this greater than any of the needs that we have for A, B, and C, or for P1 and P2? P1 and P3 because P1 and P2 is already gone. So the question is this vector greater than this one? The answer is no. Is it greater than this one or equal to? The answer is no. So here we failed to find the next process in the safe sequence. So system will become unsafe if the request is granted. That's why we have to reject the request to avoid unsafe state and possibility of deadlock. And that's it. So the last one gets rejected. As it won't pass the third item in the checklist. So I'm just gonna make that third item. So remember these three items in the checklist. If all of them are satisfied, then you're good to go. You have to accept or grant the request. Otherwise, you have to reject it. And that's basically it. Thank you for watching.